We are now in a position to start working on generalized estimating equations. To properly place it in the broader category of models for non-Gaussian longitudinal data is we have seen we have seen models of a conditional type where you either interpret or explicitly model an outcome given other models of the same subject at earlier times or different members of the same clusters, etc. In the marginal category, in the previous chapter, we have reviewed a number of models that are fully specified so that technically maximum likelihood is a possible estimation method. That may be very important in cases where you have, for example, interest in the correlation. Like in the POPs data set, you need a correlation to derive from there the joint probabilities. However, there are contexts where your question is truly longitudinal, like in the toenail data set. You're interested, and I'll draw it on the logit scale, to see whether or not the two treatment arms over time show a decreasing proportion of people with a severe infection, but they do so at a different rate. So you're interested in that slope difference, and we were able to formulate that as beta 3 is equal to 0. That's our null hypothesis. So Liang and Ziegler in 1986 have put out a technique, generalized estimating equations, to which there are several variations, and we will discuss some of those, but that can be considered, in the binary case at least, a logistic regression with a correction for correlation. The forewarning is the technique is not necessarily difficult to apply. It's not more difficult, also software-wise, than logistic regression. The interpretation of the parameters, both for estimation, so for estimation purposes, as well as for hypothesis testing, is straightforward, doesn't change versus the univariate case, but just how the method works, what are the bits and tricks and the various portions, that is a little bit more complicated. Let me make that clear in a different way. If we go for maximum likelihood, like in chapter 19, but also for the linear mixed model, we can say we have a likelihood function. From there, we derive the log likelihood. We calculate the first derivative, set it equal to 0, solve that score equation, bingo, we have the maximum likelihood estimator. And if you calculate the second derivative, from there you can estimate parameters. So likelihood theory may be difficult to use in practice because of the complexity of the likelihood function, but the principles are very well understood, very general, and many would say very elegant. It will be different here. It will be more ad hoc, but the good news is it will be relatively straightforward to use. So I'm going back to the chapter where we reviewed the univariate generalized linear model theory, and we said there and then the score equation that you find in a generalized linear model is simple. It consists of three portions: observed minus expected, the inverse of the variance, and then the model vector. Now, we could try and write the same thing, but then with the I replaced by ij. First attempt, something like this. Well, we have to be a little careful because here we seem to pretend that all the measurements are independent of each other. And that's not necessarily the case. So it's safer to do this in a vectorized way and take this away. So in a vectorized way, you say, okay, the single outcome y now becomes an outcome yi1 up until, in the toenail data set, yi7, and that's now my vector of outcomes, which I place here. The corresponding means, they follow from the logistic expression that we have formulated before, e to the power beta 0 plus beta 1 times treatment, etc., etc. You fill in the various times, the 7 times, and bingo, we're still here, you have your vector of means. Then the D matrix is the derivative of that expression with respect to the beta parameters. But again, it's of the form e to the power a function of beta, 1 plus e to the power the function of beta. So all those derivatives are remarkably easy to calculate. It's good to verify for yourself that you can do that, but it really is not very difficult. The V matrix now. The V matrix is the variance-covariance matrix of the Y's. We have the mean variance relationship, remember? So the variances are taking the form mu ij times 1 minus mu ij, filling the diagonal of the problem. But there it stops. There is no mean correlation relationship. So we don't know here and now how to get to the correlations. Something additionally needs to be done to get the correlations. So, to recap a little bit, the V matrix, if you spell it out in full, consists of a correlation matrix in the middle, and that seems the easiest thing to consider, but that's actually the one causing trouble. Whereas the A matrix to the power 1/2, what is that? Well, we sometimes call it the standard deviation matrix. The standard deviations are along the diagonal. Again, that will be the square root of mean times 1 minus mean in the binary case, or the square root of the mean in the Poisson case, etc. So that matrix depends on beta. Everything that depends on beta you have. But both the overdispersion parameter as well as the correlation matrix is new parameters, and we don't have them. So how could you get them? Well, you could start modeling them. But if you start modeling them, this model moves you straight to the Bahadur model. And that's not where we want to go. Actually, we want to avoid that. We want to keep the regression function and don't do much extra work. That's the goal. We need to do some extra work to be able not to do so much extra work. But that is what will be explained now. So let's just imagine, bingo, we found a way to do it. Well, then the following result applies. We may say then, we find, that our estimator, the solution to this problem, is consistent, asymptotically normal, with a variance-covariance matrix of which the sample version can be constructed relatively easily. However, we have to make certain assumptions, and these assumptions are relatively unrealistic. For example, the assumption is the alphas are known, and also the parametric form for the VI alpha is known. Now, what does that mean? Let's set one step back and say, okay, mathematically, it seems to be a set of regularity conditions, but what does this mean for me as a data analyst? Well, it means, thinking of the toenail data set, we go back to the doctor, and we say we have a correlation matrix here, 7 by 7, of course, with 1 on the diagonals, but what form can you propose for the alphas, and how many are there? Well, we have 7 measurements, 7 times 6 divided by 2, that's 21 different correlations. So these 21 correlations, how should I specify them? But the doctor says, okay, no problem, I can tell you, I have a lot of experience in this area, all of the alphas will be equal to the same value. And we say, okay, great, you're a really good expert, we bring a nice bottle of wine, because we have an additional question, that alpha, what value does it have? And the doctor may say, oh, you said it equal to 0.42739, and that is the value I can feel is the right value. Of course, you have been feeling for a long time, this may make no sense at all. And that's why Liang and Ziegler called this the naive method. So, yes, it would work, but under these totally unrealistic conditions, in other words, we need something else. And that something else we will move to now. So, what we now say is, we have a correlation matrix, we cannot avoid it, it contains new parameters, but those parameters do not need to be correctly specified. Working correlation matrix means it is a working version, it's not necessarily the correct version. Likely it won't be, but we don't care, because we can buy insurance against that misspecification. Okay. Small remark, actually, it would have been better to call it wrong correlation matrix, incorrect correlation matrix, but of course that doesn't sell well, people don't like that so much. Working correlation gives the impression that somehow it still needs to be correct anyway. I'll come back to that, but really in the basic philosophy, and that's what I would like to get across now, the correlation matrix does not need to be correct. So we solve these equations. Well, score equations, we should replace that term by EE, estimating equations. So it's estimating equations rather than score equations. The score equations is the first derivative of the log likelihood, but we don't have that anymore. We broke it by saying, okay, this equation kind of follows from something similar like a likelihood, but we didn't start from a likelihood. We started from the equations in the univariate case that we stretched up by making scalars equal to matrices and vectors and trying to solve that, and even with the wrong correlation matrix. So we're fiddling with those score equations up to the point that we should call them estimating equations. But nevertheless, if we solve them with a correctly specified mean function, that means with a correctly specified regression function, we still find an asymptotic normality result. But now, with the variance-covariance matrix, that's a bit more complex. It consists on the outer side of twice the same thing, and that's why we sometimes call it a sandwich estimator. In the inner side, we still have the same pieces, and that's always that model matrix at D. Remember, D is the derivative of the mean functions with respect to the regression parameters. V is the variance-covariance matrix that we have just misspecified. And then there is the variance of yi. Okay. This result is valid whether or not the working correlation is correctly specified. That's why Liang and Ziegler called it robust. Now, several remarks are in place. So, the 2 pages ago, of which we feel we shouldn't use it and therefore properly called naive, Liang and Ziegler were criticized because Peter McCullough said, hey, wait a minute, this estimator is actually coherent with likelihood theory, and you're calling that naive. So the more politically correct name that also many software packages use is purely model-based. And then here, the word robust, of course, you have to be careful. There are people in robust statistics who are very protective of their word and their terminology, so they would say, stay away from it, we were first. Liang and Ziegler said, sorry, no problem with that, and they called it the empirically corrected estimate. I must say that I personally find empirically corrected and purely model-based not so clear. You have to think about which is now the good one and which is now the bad one. Robust and naive, it's immediately clear. So I will often keep using that throughout the rest of this and the next chapter. That's one comment. Another comment is that the two estimators are the same if the variance-covariance matrix is correctly specified. So suppose that the correlation after all is correct. Well then Vi of alpha is not a guess, it's the truth. But then V inverse and the variance, they cancel. They're each other's inverses. But at that stage, I0 becomes equal to I1. I have a simplification here, and it's back to the previous 2 pages. If the working correlation would be very misspecified, there is a chance that the two variance-covariance matrices are relatively different, which is why these two matrices are often looked at together to see how close or how far apart of each other they are. But the question I have now is, wait a minute, the variance of yi here, don't I misspecify the V matrix, so the Ri matrix to be very precise? Don't I misspecify that because I cannot care to really model it correctly because it would make my life too difficult? And now I'm saying you can correct it provided you have the correct variance. Yes, but the thing is, this is a model for the correlation, or V is a model for the variance. The model can be wrong, but it doesn't mean that you cannot get access to the variance of yi. We have a very simple tool for that. Y minus mu times y minus mu prime. Y minus mu is observed minus expected, vector. Y minus mu prime is the same vector transposed. So that is a variance-covariance, that is not a variance-covariance matrix, that is a rectangular, a square matrix with symmetry also, of which the expectation is the variance. But there is actually a small problem with this guy as such. Y minus mu times y minus mu prime has the same rank as if I would calculate the rank of the two matrices reversed in different order. But that's a scalar, right? A row multiplied with a column gives a single number, and the rank of a single number is 1. So this thing is entirely rank deficient, which means that you cannot use it as a good estimator for the variance of yi. But do we need a good estimator? No, actually no. We're interested in the variance of beta hat, and that variance is the whole thing combined. So the fact that each one of the observations would be poorly estimated in terms of its variance, that's okay as long as your sample size is sufficiently large. And that's now the thing. With generalized estimating equations, we usually need a bigger sample size than with the linear mixed model. Let me make that clear. The rat data set, the prostate data set is 40 to 50 people or animals. Here, in the toenail data set, we have 400. So you typically need an order of magnitude more data, especially if the outcome is binary. So the poverty of the correction plays more with binary data than with counts, for example, especially when you have relatively long sequence, when you have relatively short sequences of repeated measures. So this would, of course, be less of a problem if you were closer to the truth. So am I saying, after all, that it needs to be correctly specified? No. There are actually, I think, 3 very important properties: consistency, asymptotic normality, and efficiency. Now, consistency and asymptotic normality are both fine, whether the correlation structure is correctly specified or whether it's not. Efficiency can be affected when you have misspecification. So, of course, that is a problem in small sample sizes, way less of a problem in large sample sizes, but it tells us that we should do a reasonable job. Assume something that is kind of plausible, but don't go as far as spending a lot of research effort in finding out which is now the correct structure. That may be overkill, really. And as we will see in the last part of the course, also when data are incomplete, we have to be extremely careful. The working correlation. How do we get to it? We now have the idea that we can get to a working version of this variance of yi. We solve the equation, but I'm still struggling with the following. Okay, the doctor is not going to tell me the exact truth anymore about the correlation because that's not realistic. The doctor may tell me, or we may jointly decide more realistically, that exchangeability is maybe not the worst thing to assume. All nice and well, but what value to take? We could agree, the doctor and I, that 0.5 is a sensible value and maybe it's not right, blah, blah, blah. But no, that's not how we're going to do it. We're actually going to let it depend on the data. If somehow we could, just like we do with the variance of yi, get a plug-in estimator for the variance, if we could do the same for the correlation, it would at least be a bit more data-driven. So we decompose the variance again in its 3 components: the overdispersion parameter, the standard deviation matrix here, and then the correlation, where the correlation alpha and the overdispersion phi are the nuisance parameters that we need. The key workhorse, the quantity of very high importance, is the Pearson residual here, because if all goes well, as we said before, Pearson residuals are very boring. They have mean 0 and variance 1. But if there is overdispersion, they may have variance greater than 1. And if there is underdispersion, they may have variance smaller than 1. So the question here is, what else can we extract from those? Well, I already said overdispersion. That will follow, and that's well known. That will follow from the residuals. But as we saw in the Bahadur model, if I take a residual and multiply it with a residual of the same subject at a different time, the expectation of that is the correlation. Aha, just like I used for the variance something with the right expectation, I can do the same thing here. And that's exactly what we are going to do. Now, there are several forms possible, of course. I can actually for example, assume, and that's a very simple one to assume, I can assume independence as a working correlation structure. And here again, don't make the mistake to say this model assumes the data to be independent. No, we plug it in knowing it's not right, and then we fix it up by the sandwich estimator. You should break the logic, you should break the thinking that what you put in as a working correlation structure is what you truly believe to be the case. Not at all. You at best hope that it comes somehow close. So under exchangeability, what do we say? We have residuals of the same subject, but at different times, and the expectation of that cross product is alpha. So what you do is you sum them over all possible pairs, you sum them over all possible subjects, you divide by the number of terms in that product, and if you spell that out a bit more carefully, that's the expression you get here. So that is a plug-in estimator. Now, there is a little bit of a problem with those residuals, right? Because why are we doing all of that with the residuals? Well, we're constructing the residuals so that we can estimate the regression parameters beta. That's what we want to do. But to get to the residuals, if we look at their expressions, we need the means. But to get to they're part of the means. But to get to the means, we actually need the regression parameters. So it is a circular relationship. To get to the residuals, we need to have those residuals. Actually, we can make the circle a little bigger and say we need the residuals to get to the alphas. But to get the residuals themselves, we need the mu's, and for the mu's, we need the betas. But we were actually trying to construct the alphas to estimate the betas. Some of the arrows have to go the other way. So to get to the mu's, we need the betas, and therefore, to get the betas, we need the alphas. It's circular. And how do we break this circular relationship? Well, start with starting values. For example, we can say, okay, let me estimate the betas with pretty much my first idea, that is ordinary logistic regression. So you get the betas. Once you have the betas, you can then calculate the mu's, the residuals, you can calculate the alphas, and with the alphas you can solve the estimating equations and get new betas, get better betas. With these betas you go round the loop and round and round and round until convergence. And that is the fitting GE schematic that is given here. So once again, you get initial estimates, for example, from ordinary logistic regression or ordinary Poisson regression. Nobody believes that this is really the right model to use at the end of the day, but it's only the beginning of the day when we got the process going. Okay, from there, you calculate the Pearson residuals. From the Pearson residuals, you can get the alphas and, for that matter, the phis. And once you have those, you can assemble the variance-covariance matrix. With that, you can solve the estimating equations, or at least do a one-step update. From the old betas, beta t here, beta 0 is the starting values, and then you get beta 1, beta 2, up until beta t here. With beta t, you then go back and you compute the Pearson residuals. You go down and up again and down and up again and down and up again until you converge. So at the very end, you can then calculate the precision using the naive or the robust standard errors. So to summarize the whole process, you start with what I'm going to call beta initial. I could call it beta 0, but I'm going to call it beta initial. Then you go through this looping thing, and you get the final estimates beta GEE. Based on beta GE, you can calculate both this and that. Naive, robust. And now the question is, what do I use at the end of the day? Beta GE for your parameter estimates, and then the robust standard errors for your inferences. And the rest you ignore. Initial estimates, don't interpret. Naive standard errors, don't interpret. That's the quick answer. However, I can go back and say, is there no use in the rest? Well, as I said earlier, if the working correlation structure is perfectly correctly specified, naive and robust would be the same. So somehow, informally, the difference between naive and robust can give you at least an idea about how close you are to the true value, yes or no. And if you can afford to do so, you could modify your working correlation structure a little bit, or you could go to a more complex one just to have a better fit at the end of the day. So that is the algorithm we go to get our GE estimates. And on that note, I would like to make a small side remark on the linear mixed model. And this may come as a surprise because we have been dealing in this entire part, especially in this chapter, in our examples with binary data, in generality with generalized linear mixed models, for which we created this extension, or rather Liang and Ziegler created this extension. But the bottom line is no normally distributed data. Well, one question is why not? Whatever we do here applies to all data type. We never said all data type, but it cannot be normally distributed. No, we never said that. It can also be normally distributed. So it could apply in the context of the linear mixed model. What is the case, though, is it may be less obvious why it's needed. The linear mixed model can be fitted, is fittable, if that would be a word, with basic tools, with REML, with maximum likelihood. It's not a matter of computational issues, etc. And we have a number of nice properties. But let's look at some of those properties. The estimate, and that was discussed by Geert Verbeke, the estimate for beta hat, is equal to the expression that I've now placed in an ellipse. And if I would ask you, calculate the expectation of beta hat, because it's an estimator, it's a remarkably easy exercise to solve. Why is that? Well, for two reasons. Not only is the answer given in the middle of the slide, but the whole thing here is non-stochastic except for the last thing. And the whole thing looks pretty linear in y. So the expectation of y is xi beta. But look at that. If I fill in xi beta here, this thing is equal to that thing inverted. They cancel, and this is why I get an unbiased estimator. So the good news is that the W matrix and the W matrix is equal to the V matrix inverted, V being ZID, ZI prime plus sigma I, which follows from the linear mixed model. It doesn't depend on it. Whether that W is correctly specified or I start again, whether V is correctly specified, yes or no, it doesn't make the slightest difference. At the end of the day, you get a consistent estimator no matter what. Yeah, but what about precision? We statisticians know that point estimates is half of the story. We want the full story. So the variance in the logic of the linear mixed model, which is maximum likelihood, it takes this form if you derive it, but then you say the variance of yi and w are each other's inverses. Where have we heard that before? This thing cancels with that thing then, for example, and you get this simplification. But this is provided that w is correctly specified. Now, if you look at that very carefully, the only problem is the assumption here that w and the variance are each other's inverses. So if w is incorrectly specified, it's not a variance, but then this expression is still correct, and that's the sandwich estimator. So if the simplification can do you harm, don't do the simplification and leave it at that. It would lose some efficiency. It's possible that it loses some efficiency. That's the price to pay. But when would this be useful? Well, think of the prostate data. You have a very small data set and a fairly complex model. You assume quadratic profiles with a random intercept slope and slope in time square. And it's almost a miracle that it works because the D matrix is 3 by 3. Just imagine that the profiles look fairly quadratic, but the model doesn't fit because your data set is so small. But in that case, you can specify a random intercept, a random slope in time square, leave out a random slope in time, you could include a random intercept and a random slope in time, not in Times Square, leave it out, knowing that it's misspecified, but you use robustified inference. Is there a price to pay? Yes, threefold. You may lose some efficiency, but you gain bias correction. You correct the bias. 1, efficiency loss. 2, no random effects to interpret anymore, because this is purely marginal. If you want to make random effects interpretations, it's quite simple. If you want to make random effects interpretations about the random effect structure, but you start from the premise that you have misspecified it, it's not going to work. That part is not going to work. There is that. And then also with missing data, you moved away from the likelihood framework, and we will see there that there are consequences. But if you say my data are complete or sufficiently complete, or we will deal with that with missing data, and my interest really is only in the marginal parameters, in the fixed effect, there is no reason whatsoever to look at variance components or to look at random effects, empirical Bayes estimates. No. Well, then you can use this version. And in SAS, you do that by including the empirical option into your model. Okay. That concludes the first version of generalized estimating equations. We will, in the next chapter, go over a variety of alternatives briefly, not as much in detail as we did here, and then take it from there and illustrate things on the toenail data set.